With exercise 2118, we're moving on from the mechanism section of the course, which was all about nucleophilic acyl substitution, and we're moving to just the synthesis section of the course, where you hopscotch from the reactants to the products, one recipe at a time. So I'm going to work these out in two ways. The first, at the beginning of each of these sections, I'm going to show you just step by step how you get the product, just thinking of it from a synthesis perspective. And then for those of you who are interested, you can stay tuned to see the mechanism for how it would work. So I'll draw in the mechanisms for these also, but I'm going to do the synthesis and the mechanisms separately. It's the synthesis that you need to know for the test. But the mechanisms hopefully will make it easier to remember what these things are because it'll make them meaningful reagents. Okay, so what do we see here? We have an acid chloride, and in fact in this video we're going to be dealing exclusively with acid chlorides. These are the most reactive of the carboxylic acid derivatives. When you see an acid chloride, you want to see the chlorine there as your leaving group. To predict your product, you're going to erase that. Okay, so you can sort of make a draft of your product just by drawing the same thing, but without that leaving group. Okay, that leaving group is going to get replaced by your nucleophile. So what is the nucleophile? LaH is lithium aluminum hydride. The nucleophile in that is the hydrogen. Now when we talk about the mechanism, I'll talk about why, but ultimately you replace the leaving group with that nucleophile. Now that's a plausible answer, but it ignores one key thing. Lithium aluminum hydride is an extremely strong nucleophile. We learned a reaction of a lithium aluminum hydride with aldehydes in the previous chapter. It reduces them to alcohols. So while it will take the acid chloride to that aldehyde, it will continue. It will reduce it again. You'll replace a bond to the oxygen with a bond to the hydrogen. And ultimately, you would have this. Well, ultimately you would have this, where you've added two hydrogens. Now there's another hydrogen on there that ultimately comes from the water, so if you're interested in where that comes from, then you can watch the mechanism part for this. But for right now, if you're just going through the synthesis, that lithium aluminum hydride replaces your leaving group with two equivalents, hence the excess, two equivalents of hydrogen. And so it takes it all the way down to an alcohol. Okay, so if you're only interested in synthesis, that's all there is for A. I'm going to talk about the mechanism for A, and if you want to go to B, you can scrub forward in the video. Okay, so how does this work? What does lithium aluminum hydride even look like? If you look at the formula for lithium aluminum hydride, you see a metal in the middle, and that metal has very low electronegativity. So you'll have four hydrogens bonded to aluminum, and a unique thing happens. Hydrogen is more electronegative than the metal, so it becomes a sort of nucleophile. It pulls electron density to itself, and the aluminum itself becomes slightly positive. Now this whole thing, overall, has a full negative charge. So to stabilize it, they bring in the lithium. The lithium cation stabilizes that anion. So that's lithium aluminum hydride, and it's basically a hydrogen nucleophile because of the polar bond between hydrogen and aluminum. So when you react that with your acid chloride, here we have this. We know that the carbonyl carbon is electrophilic, and so each of these hydrogens, these electrons, are pushing against each other. They all want to have negative charge, they all want to get as far apart as they can. The aluminum is trying to hold on to them all, but it can't, because it's not electronegative enough. So one of them gets kicked off, and it uses its electrons to act as a nucleophile to attack the carbonyl carbon. The pi electron goes up. You end up getting a tetrahedral intermediate. So let me add a page here. You end up getting a tetrahedral intermediate that looks like this. That oxygen is very unstable, and notice that we have this hydrogen that we added, that nucleophilic hydrogen. That's very unstable. It snaps back down and kicks the chlorine leaving group off. So that's how you get the aldehyde. But the aldehyde has a carbonyl carbon that is electrophilic too. So if you have excess lithium aluminum hydride, another equivalent of this can come in and the hydrogen can act as a nucleophile and attack the carbonyl again, kicking those electrons up. So what you get after that second nucleophilic attack is another hydrogen in addition to the first one. The oxygen now has a full negative charge, kind of like in the tetrahedral intermediate before. But before, there was a good leaving group, and now there is no good leaving group. The hydrogens are not going to come off of that molecule. They would not be able to stabilize a negative charge in their tiny, tiny space. It's the smallest atom on the periodic table. So the best you can do is to stabilize this charge by doing a proton transfer. And that's what this water is for in the second step. So you'd have water, and this is going to be in equilibrium. Both of these oxygens want the hydrogen, but the negative oxygen, the full negative oxygen charge, can kick the hydrogen off. The electrons would go on to the oxygen and water, and you would have your alcohol. Now the hydrogens are still there, but remember, in these skeletal structures, they're implied, so most often, especially on standardized tests, those would not be written in. And so that would be your product. Notice that's that alcohol, that primary alcohol that we predicted in the beginning. Okay. One key thing to note here is that lithium aluminum hydride is a strong hydrogen nucleophile. It adds hydrogens, and it does it as many times as possible. It won't just react with the carboxylic acid derivatives, it will also react with aldehydes and ketones. Okay, let's try this one. It actually gives us the same carbon chain, and now first I'm going to think about this from a synthesis perspective. Then I'm going to think about it from the mechanism, from the perspective of the mechanism. So from a synthesis perspective, I look at this, I see the chlorine is my leaving group. So I'm going to try, just as a rough draft, drawing in my product. So the chlorine won't be there, and what will replace it is my nucleophile. Now you know that something here has to be your nucleophile, but if you look at it, you see a metal again, the magnesium, that gives its electrons away. Whatever it's bonded to becomes negative, and that's this pH here. Now that pH is a benzene ring acting as a branch. We've seen that before in, for example, and actually let me draw this in. So this would be like that. We've seen this pH before in the Wittig reagents, where we had triphenylphosphine. We used that to make Grignard reagents, where all of these were benzene rings. Okay, so this is a Grignard reagent here, and we're going to replace our leaving group with our nucleophile, which is a benzene ring. That's the pH. So this will come in, and we'll have that. That's a plausible answer. And you do get that, but it does not stick around for very long, because just like lithium aluminum hydride is a strong hydrogen nucleophile, these Grignard reagents are strong carbon nucleophiles. And so a second equivalent, and that's suggested by this excess, a second equivalent adds. When it attacks, you end up putting, you just have one bond to this, you end up putting a second benzene ring here. And the water fills in the hydrogen in the second step, just like in the mechanism for lithium aluminum hydride. So that's your product. Okay, that's just looking at this from a synthesis perspective. What's the mechanism for this? So I'm going to go over that now. If you want, if you're not interested, you can skip to the next. You can, when you see C, you can scrub until you see C on the screen. But for now, we'll talk about how this works in terms of the mechanism, just really quickly. So we have our acid chloride. We know that the carbonyl carbon in that is electrophilic. So if you have a carbon nucleophile, like we have here in phenylmagnesium bromide, the bond between the carbon and the magnesium is really almost an ionic bond. It's not quite, but it's almost. The carbon steals the electron density a lot, and the magnesium almost has a full positive charge. That's stabilized by the bromine. And when you put this into a solution, these separate, and the Grignard reagent can attack the electrophilic carbonyl carbon. So this attacks here, kicks the pi bond open, you get your famous tetrahedral intermediate. This now has a bond to the benzene ring, just one oxygen on top there. Famous tetrahedral intermediate, this negative charge is flapping in the wind, very unstable, so it snaps back down and kicks the best leaving group off. That's the chlorine. So nucleophilic attack, and then here, loss of a leaving group. And what we have, oops, and there's this methyl branch here. So what we have is one nucleophilic acyl substitution. We replaced the chlorine with the benzene ring. That was what we predicted here at first. But we don't stop there. We have excess phenylmagnesium bromide, and so another equivalent of this nucleophile is present. The phenyl ring, the benzene, is able to attack this carbonyl carbon again because it's slightly positive, kicks the electrons up, and what you immediately form is again a tetrahedral intermediate. Now we have two benzene rings, or if you prefer, phenyl branches on that carbon. The oxygen has a negative charge, so it's similar to the tetrahedral intermediate we had before, but the difference is that before we had a good leaving group, and now we don't have any leaving groups. So the negative charge can't snap back down. The best you could do is a proton transfer from water. That's why water is the second step here that we see, the second step. So the proton transfer from water, here this negative oxygen steals this hydrogen, the electrons would go back onto the oxygen there, and you'd be left with an alcohol. Oops, this should be there. So, ultimately, you would have this molecule here, which is what we predicted up above when we were just thinking about this from the perspective of synthesis. So, Grignard reagents, thing to remember, Grignard reagents are strong carbon nucleophiles. They will add as many of themselves to an acid chloride as they possibly can. So watch out for that excess there. All right, in C. So in C, first I'm going to think about this just from synthesis, and then we'll discuss the mechanism. So from synthesis, you would look at the carbon compound, you'd recognize you have an acid chloride, and the chlorine is going to be a good leaving group. So one plausible thing is to redraw the carbon skeleton just without the chlorine for the first step. You'll notice we have 3 steps here. So in that first step, we're going to replace the chlorine with whatever our nucleophile is, and that is a hydrogen. This, if you look at this carefully, you'll notice it's very similar to lithium aluminum hydride. Lithium aluminum hydride, as we discussed above, is a strong hydrogen nucleophile, and this weakens it. I'll discuss why when we talk about the mechanism. But this lithium aluminum trialkoxy hydride only adds 1 hydrogen. So you wouldn't reduce this further if that were the only thing you were adding. So that hydrogen nucleophile replaces our leaving group. Okay? Now, we're at the previous chapter. We have an aldehyde. How does an aldehyde react with a Grignard reagent? And here, ethyl, that's CH3CH2, and then MgBr. Well, this is a carbon nucleophile. Our carbon here is going to attack the carbonyl. And so it'll attach there, and it'll attack. So 1, 2, right? Those are our 2 carbons. and then you have the oxygen on top, which gets a hydrogen from water. So just in terms of synthesis, I'm going to redraw this as, this is the same as this. I'm just not going to draw the hydrogen in. And I'm going to draw the ethyl group with more conventionally. So that's your product, your predicted product, that alcohol there. That's this reaction from the perspective of synthesis, recognizing these recipes. Now, if that didn't make sense, let's talk about the mechanism. So, for the mechanism for this one, lithium aluminum hydride had the aluminum in the center, 4 hydrogens bonded to it, and because hydrogen is more electronegative than any metal, it pulled electrons to itself, and the hydrogens became slightly negative. And the aluminum lost those electrons, became slightly positive. The whole thing had a negative charge that was stabilized by the positive lithium. So that's lithium aluminum hydride. This was a strong reducing agent, a strong hydrogen nucleophile, because aluminum is not very electronegative, and so it gives a lot of electron density to the hydrogens. Well, what if we want to weaken this? What if we want this to be a weaker hydrogen nucleophile? We can, instead of having 3 other hydrogens here, we can use electronegative elements. So, for example, like oxygen and some R group, it doesn't matter what the carbon chain is, it's the oxygen here that's going to be making this impact. The oxygens are electronegative. Now, usually you think about that as acting over one bond, and it's true that the effect of electronegativity gets much weaker as you go more than one bond away, but it can still act in a significant way 2 bonds away. So these oxygens don't just pull electron density from the aluminum, they also pull some electron density from the hydrogen. And that, as the electron density moves away from the hydrogen, the negative charge on the hydrogen becomes smaller. And so it becomes a weaker nucleophile. So whereas lithium aluminum hydride will not only react with carboxylic acid derivatives, it will also react with aldehydes. This trialkoxy, right, I have 3 alkyl groups bonded to oxygen, trialkoxy, this lithium trialkoxy aluminum hydride will only add 1 hydrogen to the acid chloride. It won't react with aldehydes or ketones. So if we start with this acid chloride, then what we see here is this hydrogen, this weakened hydrogen nucleophile, attacking our carbonyl carbon, which is slightly positive. And the pi bond breaks, the electrons go onto the oxygen above. You get your famous tetrahedral intermediate. So we have that hydrogen bonded there now. This oxygen has a full negative charge flapping in the wind, very unstable, so it snaps back down and kicks the chlorine off. So loss of a leaving group. And what we've done by adding that lithium trialkoxy aluminum hydride is turn the acid chloride into an aldehyde. We added 1 equivalent of a hydrogen nucleophile. So that's the first step. And notice how it's written here. Lithium, aluminum, the OR in parentheses with a 3 outside, and then the hydrogen. The second step, we added ethyl magnesium bromide. Now the ET stands for CH2, so we've drawn that here. If we take this aldehyde and react it with this ethyl magnesium bromide, this is really almost an ionic bond. The carbon there has almost a lone pair and a full negative charge, and the magnesium would have a full positive charge. So the carbon can act as a nucleophile, attack the carbonyl carbon, kick the electrons up, and you would get something very similar to our tetrahedral intermediate. You would get an ethyl group bonded, and then the O. Now notice, we had 1, 2 carbons, we have 1, 2 carbons that we added. So this is very similar to the tetrahedral intermediate we had above. The one big difference is that that one had a leaving group, so the oxygen could come back down and recreate the carbonyl. We do not have any leaving groups here. Carbon and hydrogen don't act as leaving groups. So the best you can do is stabilize that negative charge with water. And that's why water is given as this third step. In general, after you react lithium aluminum hydride or Grignard reagents with a carboxylic acid derivative, you'll want to follow it up with a water wash to stabilize the molecule. So you could have this. The negative oxygen would steal one of those slightly positive hydrogens, and I'm really just drawing these mechanisms quickly, but in general, the idea you would get would be this. And I'm omitting the hydrogen because that's implied in these skeletal structures. So you have 1, 2 carbons, 1, 2 carbons attached to the one with the oxygen. All right, and that is the product that we predicted up here in the synthesis step. Okay, next one. So D. Now first I'm going to think about this from the perspective of synthesis, and then after that I will look at the mechanism. So looking at this from the perspective of synthesis, I notice that the carbon molecule we start with is an acid chloride, and so the chlorine is a leaving group. So one sort of rough draft for the first product you would make from that is to redraw the molecule just without the chlorine, which is going to leave, and then add in your nucleophile. And what we have here is a metal. If nothing else, you would recognize the copper as a metal. If you compare where copper is on the periodic table to where magnesium is, it's much further to the right. Magnesium is all the way to the left in group 2A, and the copper is one of the transition metals. So it's much further to the right than the magnesium is, and therefore it's more electronegative. So this is something called a Gilman reagent, and I'll discuss it in more detail in the mechanism, but the general idea is the nucleophile is whatever is bonded to the copper. And here that's an ethyl group. So our nucleophile is effectively this ethyl group. So we're going to add 2 carbons, replace the chlorine with 2 carbons, so 1, 2. Now, if that looks like 3, just keep in mind, it's 2 there. We just had to add that bond to connect it to the carbonyl. So that's what you would expect after that first reaction. And one thing you really want to remember is that these copper-lithium carbon nucleophiles, they're called Gilman reagents. They're just like Grignard reagents, but they're weaker. They will only add 1 equivalent of the carbon nucleophile. A Grignard reagent would add it all the way down. It would react with a ketone. These Gilman reagents won't. Okay, so that's what we get after the first step. After the second step, we'd see lithium aluminum hydride. We would know from the previous chapter that that reduces a ketone to an alcohol. Secondary ketone to an alcohol. It replaces a bond to an oxygen with a bond to a hydrogen. The water at the end just puts a hydrogen on that oxygen. So that would be the product you'd predict. Okay, let's take a second to think about the mechanism of how that happens and how these reagents are working. Hopefully that will help you remember them. So the first one is this lithium dialkyl lithium cuprate, as it's sometimes called, the Gilman reagent. So you have copper. Copper is being stabilized by the lithium, and it sort of forms a compound with it, and then to that we have 2 ethyl groups. Now each of these ethyl groups is separate, so one ethyl group going in one direction, one ethyl group going in another direction. You'll notice it's ethyl because you have 2 carbons. So let's just next to this, compare this with a Grignard reagent. What if you had an ethyl group bonded to a Grignard? Magnesium has very low electronegativity, so the partial charge on this carbon is really big. And the partial charge on this magnesium is also really big. The magnesium just can't hold on to its electrons. The copper is much further to the right on the periodic table, so it's much more electronegative. And that means that it can hold its own in this tug of war for these electrons better than the magnesium can. The carbon only wins a little bit, and the slight charge is smaller. So in the charge on the copper would also be smaller. In other words, these copper-lithium reagents, these Gilman reagents, are weaker carbon nucleophiles. You can see how big the charge is here. We often just draw it as a full negative charge in a Grignard reagent, and you can compare that with how small it is in the copper-lithium reagent. And that means, just like with the lithium-aluminum trialkoxyhydrides, only one equivalent of the nucleophile will attack. This will only react with strong electrophiles like the carboxylic acid derivatives, acid chlorides, and anhydrides. It won't react with aldehydes or ketones. So when we take that and we combine it with our substrate, this substrate here, the slightly negative carbon acts as a nucleophile, takes its electrons, and acts as a nucleophile to attack the carbonyl carbon. That kicks the pi electrons up, and you end up with a tetrahedral intermediate. So the oxygen going up, now we have this ethyl group, so 1, 2, and we have the chlorine still. Now that oxygen has a full negative charge flapping in the wind, very unstable. To stabilize itself, it snaps back down and kicks the leaving group, the chlorine, off. So what we end up with after reacting our substrate with our acid chloride with the Gilman reagent is this ketone here. So that's the first step. In the second step, we have lithium aluminum hydride. So if you recall, lithium aluminum hydride has the aluminum bonded to 4 hydrogens. The whole thing has a negative charge stabilized by the positive charge of lithium. Each of the hydrogens has a slight negative charge and can act as a nucleophile. Here it would attack this carbonyl carbon, kick the pi bond up, and so you would have another tetrahedral intermediate. But here, there's no good leaving group, unlike before. Before we had a chlorine that the negative oxygen could kick off. Here, none of these things are going to get kicked off. Carbons and hydrogens are terrible leaving groups. So the best we can do is add a water to stabilize this negative charge with a proton transfer. So if you look here, our third step is water, and what that's doing, as it's done in the previous reactions, is just putting a hydrogen on that oxygen to stabilize the charge on it. And so you end up with the alcohol. And that's what we predicted above, this molecule here, we predicted in our synthesis step. Okay, how about E? Now with E, again, I'm going to look at this first as, first just from the perspective of synthesis, and then we'll take a second to talk about the mechanism. So here, I look at the carbon chain that I have, and I have an acid chloride, carbon double bonded to oxygen, single bonded to a Cl. So you've got the chlorine there. We're going to replace that chlorine with our nucleophile. In this thing, the nucleophile is really the oxygen, but it's going to carry the rest of the molecule with it. So, well, we could, as a rough draft, we could redraw the molecule, just replace the chlorine with the oxygen there. Now, you might be tempted to include the hydrogen. Notice that would have 3 bonds to the oxygen, so the oxygen would have a positive charge. It does a proton transfer to get rid of that. And so that's your final product. Okay, that's it. However, that's it from the perspective of synthesis. How does this reaction happen in terms of the mechanism? And it happens through a nucleophilic acyl substitution reaction. So to avoid drawing these benzene rings, I'm just going to write them as pHs. So pH, chlorine, that. Notice capital P, lowercase h. That's a benzene ring, acting as a branch. So here, if you have that, and the other molecule is an alcohol, so this here is this molecule, the slightly negative oxygen can attack the carbonyl carbon, kick the pi bonds up, you get the tetrahedral intermediate. And this is happening because this oxygen is slightly negative and this carbon is extremely reactive. So you end up with the famous tetrahedral intermediate. oxygen has 3 bonds, and so a full positive charge. This oxygen only has 1 bond, so a full negative charge. The oxygen with a full negative charge snaps back down, kicks the chlorine off. So I know I'm going through these mechanisms really fast, but that's because they're not the focus here, and because we've spent so much time on them in previous videos. So we have this here. Now we're almost done. We just have this hydrogen here with the full and the oxygen has the full positive charge. So we need to stabilize that. And that's what this pyridine is here for, this other molecule that they include in the recipe. Pyridine is sort of the nitrogen version of benzene, although I should say it's more like benzene if you replace 1 carbon with a nitrogen. Now you'll notice that, so that's pyridine. This is pyridine. So it's an amine, kind of. You replace one of the carbons in benzene with a nitrogen. You'll notice that this ring is aromatic, just like benzene is. It has 2, 4, 6 electrons in the ring system, in a conjugated ring system, and so that's aromatic. Now, because that's aromatic, these electrons in that lone pair are not included in the aromaticity. That would give you 8 electrons, which would be anti-aromatic. Besides that, you're already using the py orbitals that you would need to create the pi bond. So there's not a second py orbital that these can exist in. They point out into space in a hybridized sp2 orbital. So they're basic. In other words, they're able to accept H pluses. So just like ammonia would. So pyridine can act as a base, accept this H plus, kick the electrons back, and you end up with the product that we had before. So first I'll draw it with the pHs, then I'll draw the rings out. So that's sort of the abbreviated version. And then we have a pyridinium ion, which would look like this. This is just a side note though. So that nitrogen has 4 bonds, and so a full positive charge, that's pyridinium. Actually, you know pyridinium, because pyridinium is the P in PCC. Pyridinium, PCC stands for pyridinium chlorochromate. So you have the pyridinium there, which is stabilizing a chlorochromate. So chromium there. And there are, and there's a negative charge in that chromate that the positive charge in the pyridinium is stabilizing. Okay, anyway, that's not the focus here, but there it is, a cameo, pyridinium, showing up again. The way that would look like, if I redrew all this out, remember the pHs are standing for phenyl branches. Those are benzene acting as a branch. So redrawing this out, you would have this product, which is the same thing we predicted about in just the synthesis step. All right, so next and lastly for this video is this exercise in F. First, let's just think about this from the perspective of synthesis, and then we'll walk through the mechanism. I see the molecule on the left. I see an acid chloride, carbonyl bonded to a Cl. The chlorine is a leaving group. So as a rough draft, a possible product could be the same thing, just replace the leaving group with your nucleophile. And your nucleophile is the nitrogen in that molecule. So you could replace it there. You might be tempted to put the hydrogen there, but you'll notice that gives the nitrogen 4 bonds and a full positive charge. So you do a proton transfer to get rid of that. And that's your final product. Now, that happens through a nucleophilic acyl substitution. Very similar to the one we had before. I'm just, again, going to draw the benzene ring as a pH. So we've got that chlorine there. Here we have our nitrogen. The nitrogen has 3 bonds and 1 lone pair. It's slightly negative because it's electronegative, so it can act as a nucleophile to attack the carbonyl carbon, kick the pi electrons up, and we get, after that nucleophilic attack, we get a tetrahedral intermediate. Chlorine is still there. Now we have this nitrogen, which has 4 bonds, and therefore a full positive charge, and an oxygen, which has only 1 bond and therefore a full negative charge. Well, that tetrahedral intermediate is very interactive, or very interactive. It's very reactive, and so this snaps back down, kicks the leaving group off, and you pretty much have your acyl substitution. The only thing is the nitrogen has that hydrogen there. It still has the 4 bonds and the full positive charge, and so that's why you're using 2 equivalents here. These 2 equivalents you're using because another one of these amines comes by, and they has the lone pair there that can act as a base. Steals the hydrogen, electrons snap back, so you're ultimately left with your final product, which would be, first I'll draw it with the pH and then I'll expand it out. So that is your final product, and so remember that pH is really just a benzene ring. So that is the product you'd predict, and that's the product we did predict in the synthesis step above. So hopefully this video helps you a little bit with thinking through synthesis questions that involve acid chlorides, the most reactive of the carboxylic acid derivatives.